Good evening, viewers, and welcome to this session on multiple regression and hypothesis testing. You are all already aware from your study of MEC 009 and also a course of your first year MEA, MEC 003, that under statistical inference, two aspects of estimation and hypothesis testing are very important for us. Here in this particular session on multiple regression, we will be seeing how those two things will be particularly applied in a situation where we will be attempting some modeling called regression models. Under this, we will be coming across various aspects like what will be our dependent variable and what will be our independent variables and how many of them should we include and what should be the form of our modeling. And having done that, can we allow for non-linearity to be there? And if we do that, can we afford to have it both for parameters as well as variables, or can we do it only under some restrictive considerations? These are the things that are there in front of us, and we then would have to know on the estimation side, how are we going to estimate the parameters that we will include in the model. And if we do that, and if we do the job of estimation, we are naturally involved in a situation of testing whether they are good, whether they are acceptable at a certain level that we call as test a level of significance. These are the aspects that we come. Then there are questions of what variables to include and what should be an yardstick which will guide us in the inclusion of some variables to those of the others. And since we cannot measure exactly, accurately, which is one of the basic economic limitations, and since we have no way by which we can include all the variables that we ought to be including, we also have to make a provision for all those variables that we cannot include in the name of a error term or a residual term. If we do all this, the basic questions that come in front of us are those of estimation and hypothesis testing. With this thing in our mind, we have decided to devote this particular session on the problems of modeling and the two specific things that come under that, namely estimation and hypothesis testing. I have with me to conduct this session an expert, Dr. B.S. Bagla, who has been teaching in Delhi University for the last 30 years in various branches of discipline. I welcome Dr. Bagla for this session.
Thank you, Prakash.
And I request him to tell us something about the various issues that are involved in this particular subject, taking us through in stages and helping us to get a conceptual and analytical understanding that is required very much in our various tasks that we carry out in economics. Dr. Bagla, please.
Thank you, Prakash. Viewers, I would like to refresh your knowledge about regression analysis, classical linear regression model first. It is basically a two-variable model. One variable, y, is dependent variable and the variable x is independent variable. We have population regression function with us. This is the relationship as we expect would be present. But we do not remain satisfied with the mathematical specification, which is y equals b0 plus b1x. We rather prefer to operate with stochastic specification of this very model. Here we have included the term ui, which is the stochastic term. This term ui needs some explanations, some elaborations. It includes influence of all the variables which have not been included in the model. Even if all the variables are included, some randomness may arise on account of human behavior. After all, human behavior is not always according to a set of rules and regulations. Some kind of human judgment, human errors will also be present there. Then comes errors of measurement. Whatever variables we are considering, some errors of measurement will always be present, however precise we try to be. And moreover, there is the principle of Occam's razor that requires us statisticians and econometricians to keep the specifications as simple as possible until it has been proved inadequate. Okay, so we try to manage with as small a number of variables as possible unless some specific requirement is there to include more variables in the model. Right? So this is the nature of UI term. It includes all the variables which have been excluded from the model, which have not been considered specifically. Therefore, this UI term plays a very significant role in our linear regression model. At any point of time, we do not have the entire population space with us. All the observations in population are never available to us. We have at best a small number of observations out of that population, and that set of small number of observations is called a sample. So what we really estimate is sample regression function. Notice I've used slightly different symbols here. Y equals B0, small case b, I've used over here, plus B1x plus EI. Now I've replaced UI with EI. How do we estimate it? We estimate this sample regression function by minimizing sum of squares of errors. EIs represent errors. We transform B0 plus B1x to the other hand side, square the things and add up. This gives us the sum of square of errors. We equate first order derivatives of this sum of square of errors to 0, and that gives me the two normal equations. You can see the two normal equations here on the screen. Sigma y equals nb0 plus b1 sigma x, and sigma xy sigma xy equals b0 sigma x plus b1 sigma x square. If we solve these equations simultaneously, we'll be able to obtain estimates for b0 and b1. The estimated b0 will be nothing but the intercept parameter, and b1 will be the slope parameter for the sample regression function. One more thing is there which I would like to point out. In many cases in economic problems, we do not pay much attention to the intercept part. The slope parameter is regarded as really important. It shows the impact of or influence of the x variable on variable y. Once we have carried out this estimation, we have to make certain assumptions in order to move further. First and foremost assumption is that variable x is uncorrelated with u's. That means expectation of, and further, second assumption is expectation of ui equals 0 and variance of ui is equal to sigma square. Covariance of ui uj when I is not equal to j is equal to 0. What is significance of these assumptions? We basically want to make one particular point, that magnitude of the error terms is not related to the magnitude of the x variable which has been included in the model. Second point which we wish to make is sum of the error terms will always be equal to 0 and their variance is constant. This assumption of constant variance helps us in the inference at many stages. We also call it the assumption of homoscedasticity. That means all the error terms are distributed with the same variance. They are equally distributed. They have similar distribution. And the fourth assumption of covariance being 0 is also significant. That means error terms are also not correlated with one another. That means, say, fifth error term is not related to the fourth or to the sixth. They are independent of one another. If all these assumptions are satisfied, we can say that our error terms are independent and identically distributed random variables. With those assumptions in place, we are able to calculate variances of B0 and B1. Variance of B0, as you can read out from the screen, is ratio of sigma x square to n times sigma x minus x bar whole square multiplied by sigma square. Now this sigma square which I am multiplying herein is nothing but variance of u terms. And standard error of the estimate B0 is nothing but square root of the variance of B0. Similarly, variance of the slope parameter B1 turns out to be sigma square divided by sigma x minus x bar whole square. And its standard error will be square root of the variance noted above. We make use of these values to infer about the parameters B0 and B1. Why? Why do we have to infer about them? We have fitted a model, we have carried out the calculations, we want to know whether this model actually describes, is very close to the population model. From the sample model, we want to infer about the population. Right? One problem which we have to face many a times is that population variance is not known to us. In that situation, we try to make do with sample variance. And sample variance, my previous slide shows us S square, last line, S square, the sample variance, equals sigma ei square divided by n minus 2. This n minus 2 is degrees of freedom, okay, and numerator is called residual sum of squares. This is regarded as an unbiased estimate for the population variance sigma square. Now comes the hypothesis. Our H naught or null hypothesis is that the variable x has no effect whatsoever on the variable y. Or practically speaking, that would imply B1 equals 0. If B1 follows normal distribution, our test variable will be z equals B1 minus B cap 1 divided by standard error of B1. This would be distributed as a normal variable. However, when S is used in place of sigma, the test variable is distributed as T with n minus 2 degrees of freedom. Now, how do we make use of that T variable? You are familiar with T table, students' T distribution table. Usually we make use of 5% level of significance. That means we are prepared to tolerate an error in 5% of the cases. In 95% of cases, we would like B1 to be as close as possible to capital B1. That means we want our sample slope parameter to be as close to the population slope as possible in at least 95% of the cases, right? If you look at the T tables, you'll find that for degrees of freedom exceeding 25, degrees of freedom exceeding 25, if value of this test parameter T, which you have calculated, is 2 or above, the hypothesis can be rejected straight away. And if the degrees of freedom are between 5 and 25, and the calculated value of the T parameter happens to be between 2 and 3, then we can with all confidence reject the hypothesis. Rejecting the null hypothesis implies that we are rejecting the statement that variable x has no effect on y or has no influence over y. That means the model which we are hypothesizing is acceptable, is true, represents a pretty close picture of the population relationship. We also have another statistical tool over here which is available to us to infer about the effect of variable x on y, and this is called coefficient of determination. We know that total sum of squares, which is nothing but y minus y bar whole square added up together, is equal to the explained sum of square plus the residual sum of squares. Explained sum of squares is what is explained by b0 plus b1x, and residual sum of squares is the sigma e square, in fact. Thus, explained sum of square by total sum of squares is called r square, the coefficient of determination, and it turns out to be the square of the coefficient of relation between x and y. In the best situation, when our model is the perfect one, r square would be very close to 1. That means higher the value of r square, better is the fit given by our model, our hypothesized model, to the population relationship. Our sample regression function will be very closely mimicking the population regression function in that case. And smaller the value of r square, our model will have poor fit, will be a poor apology for the relationship between the independent and dependent variables. With these remarks, we move on to reporting of regression results. How do we usually present the regression results? We have the estimated values of y equals estimate of b0 plus estimate of b1 xi. Underneath estimate of b0, I've left out two brackets, one for standard error of b0 and the other is for t value of b0. Similarly, under estimate of b1, I have two brackets, one is for standard error and the other is for the t variable. On the side, I have left space for r square and degrees of freedom. So whatever be your regression problem, once you carry out the estimates, you have to present your results in this format only. This sums up everything which is there to know about these regression equations which we have estimated, and the information which you have over here on screen is sufficient to conclude whether the sample regression function is giving a close approximation to the population regression function. With these bits of revision, I would say, remarks for revision, I pass on to multiple regression of y on x1 and x2. Notice, population regression function in its stochastic version would be b0, b1 x1i plus b2 x2i plus ui, and corresponding ordinary least square sample regression function will be virtually the same, but capital B's are replaced by lowercase b letters over here, and ui is replaced by ei. Now, what we have done over here, we have included two explanatory variables specifically in the model. Recall the remarks made by Prakash and also me earlier on that the error terms include influence of so many other variables. Now what are we doing over here is we are ferreting out one variable x2 from the error terms and including it specifically in our regression model. What happens in this case? How do we estimate it? And what are the assumptions related to it? Notice these assumptions, they have increased in number. Now we have 5 assumptions, not 4. First assumption is what it was. Earlier on, I said X was uncorrelated with U, but now both X1 and X2 are uncorrelated with U. My second assumption was expectation of Ui was equal to 0. That stands that Ui is still incorporating influences of innumerable variables, and its expectation still remains 0. I'm sticking with my third assumption also. Ui is a constant and variance of Ui is a constant and it is equal to sigma square. That homoscedasticity stays here as well. Covariance assumption is also there. There's no autocorrelation, that is, there's no covariance between Ui and Uj. But one more assumption I'm adding over here now. Absence of linear relationship between the two x variables. This is something new. This is also called the assumption of there being no multicollinearity. Multicollinearity is absent, and this assumption is critical for estimation of linear multiple correlation model. Here we have to ensure that our estimation procedure will take care of is looking for one single linear relationship, and that linear relationship is between variable y and the two variables x1 and x2. Linearity is with respect to variable y only. This relationship is not being complicated by any other supplementary linear relationship between the variables x1 and x2. So this is the significance of the fifth assumption. What is the procedure for estimation? Here too we have to minimize residual sum of squares. Compare this expression with what you had for simple linear regression. Now you find on the right hand side the term b2x2i included within the bracket. We again differentiate the function on both the sides with respect to b0, b1 and b2 now, and this gives me 3 normal equations. Earlier on we had 2 normal equations, now we have 3 normal equations, and when we solve these 3 normal equations simultaneously, we will get estimates of b0, b1 and b2. Look at these expressions. b0 is still equal to y bar minus b1 x1 bar minus b2 x2 bar. But expressions for b1 and b2 have become more complicated. Notice one more thing. In these expressions, we have made use of lowercase letters y and x. These lowercase letters y and x represent deviations from their respective means. So in the expression for b1, top left hand corner expression reads bracket sigma y x1 bracket closed. This y is capital Y minus y bar, and x1 is x1i minus x bar is product of the two which has been added together in this small expression. The second expression is sigma x2 square, that is x2 minus x bar whole square, and all those squared values have been added up over here. This way each of the components of the expressions for b1 and b2 have to be rewritten, reinterpreted. And mind it, if we add more variables, these expressions will become all the more complicated. We are also reporting the variances for B0, B1 and B2. Here the expressions are a mixture of capital X and lowercase x and y letters. These are again, capital X's are straightforward ordinary variables as they have been provided to you, but lowercase letters represent deviations from the respective means. These expressions are much more complicated than was the case with variances of B0 and B1 in simple regression model. With the help of these very expressions for variance, we can calculate standard errors of these estimates. Those standard errors will be respective square roots only. We have the concept of R square, the coefficient of determination here as well. That remains ratio of explained sum of squares and the total sum of squares. This is also equal to 1 minus ratio of residual sum of squares to total sum of squares. This concept is parallel to the concept for simple regression model, but we have one more additional complicating concept, and that is adjusted R square or R bar square. What is it? It has been noticed that as we add more and more explanatory variables, R square keeps on rising. R square goes on increasing even when the variable we include does not really add to the explanatory power of the model. That variable may return a coefficient which is totally insignificant. The variable may be absurd in nature, yet the R square will increase. So this R bar square is an innovation which has been introduced by econometricians to rule out the possibility of inclusion of absurd variables on the explanatory side. This R bar square is calculated as 1 minus brackets 1 minus R square multiplied into n minus 1 divided by n minus k. K is the number of parameters which have been estimated in any of the regression equations. Now notice one thing, R bar square is related to R square, but the adjustment has been made for number of parameters that has been calculated from here. And usually magnitude of R bar square is less than the magnitude of R square. That is the cost which you have to incur by, in terms of the efficiency of the model, by including larger number of variables in the model, right? In some of the rare cases, R bar square may become even negative, though R square by its very nature, by its very definition, is never negative in magnitude. How do we report the regression results? The same system will be adopted here too. Y equals B0, but underneath there will be two brackets, one for standard error of B0 and the other one for the t value. Then plus B1 x1 and two brackets, one for standard error, the other for t value, and then plus B2 x2 underneath two brackets. On the side we will be reporting R square, R bar squares and degree of freedoms both. That will complete the presentation of the regression results. Our next problem is test of hypothesis for multiple regression, but I would like to face the questions, if any, from the audience at this stage.
Well, in the system that we have, although we say students can interrupt us with questions. It's not often that we get questions, but I would like to add one or two small points here, that when we have to make a choice in the inclusion or the exclusion of variables, this adjusted R square also plays a role there. I believe you know that if the calculated value of the T ratio is more than 1, that gives us a clue that we can retain that. And in terms of the adjusted R square, if the value of that calculated with the inclusion of a variable is higher than without that, that gives a clue that it can be retained or dropped.
If R bar square improves with inclusion of the variable, then definitely that calls for inclusion of that variable, retention of that variable in the model.
And possibly we can add another thing here, that two regression results we will be able to compare even if the independent variables are not the same in number with the help of the R bar square, but not so with the R square.
R square, that's true, that's true.
So these are two additional usages which are there with R bar square. So perhaps we can now continue with some of the violation of assumptions and what happens if we do that, or if anything else.
Prakash, I would like to spend a couple of minutes
Yes.
on test of hypothesis.
Yes, sure.
First, testing hypothesis regarding effect of say x1. Procedure same. Divide the calculated B1 value by standard error. Okay, that will be distributed as T with given degrees of freedom. Compare with calculated T values. If your calculated value is substantially higher compared to the tabulated value, you reject the null hypothesis of B1 being equal to 0. Same you do for B2. If your calculated T ratio turns out to be higher than the tabulated ratio at 5% level of significance, you can conclude that B2 or the variable x2 definitely has some influence on the variable y. Now since two variables are there can be a joint influence of the two variables also, and that also can be incorporated as a kind of null hypothesis. Here the null hypothesis will be B1 equals B2 equals 0. That means together these variables have no influence whatsoever. Here we can make use of R square. This tantamounts to saying that R square is equal to 0. Or alternatively, we can make use of F test. F is the variable with estimated sum of squares or explained sum of squares divided by degrees of freedom divided by residual sum of squares divided by its own degrees of freedom. Now numerator has n degrees of freedom and denominator has d degrees of freedom over here. They have different degrees of freedom. Again, you compare at different level of confidence with the tabulated values and come to the conclusions about whether the joint effect hypothesis is to be accepted or not. I would like to revisit the assumptions. Last assumption first, the multi-collinearity. In the extreme case, when variable x1 and x2 have an exact linear relationship with one another, what can be the complication? Complication could be it would not be possible to estimate B parameters at all. Notice in B1 and B2 you had a common denominator. That common denominator had the same terms, and that common denominator will be reduced to 0 if x1 and x2 were exact linear transformation of one another. But essentially in sample the problem may be that some relationship between x1 and x2 is visible. It may not be exact linear relationship, but some relationship may be present. In such cases, what happens to the estimated coefficients? They still remain best linear unbiased estimates. Large standard errors of ordinary least square estimates is one practical consequence. Wider confidence intervals may have to be designed for that. T ratios, some of the T ratios may turn out to be insignificant. Estimates may turn out to be very sensitive to small changes in data. Signs of some of the regression coefficients may not be intuitively acceptable, or you may find wrong signs of the regression coefficients. And there may be difficulty in estimating contributions of individual variables to the regression. What can be the solution to this problem? Some of the X variables may be dropped. Another solution could be try to get additional data, because we have seen many cases where multicollinearity is found in a small sample. If larger sample is taken, a bigger sample is taken, then impact of multicollinearity is substantially reduced. Altogether, new sample may be taken. Maybe the next sample will be more random, and that problem will not be present in that. Or there may be some rethinking about the composition of the model. Sometimes using some prior information about the parameters will be useful, or alternatively, variables can be transformed. You may use logarithms of variables. And in extreme case where too many variables are present, to overcome the problem of multicollinearity, we can resort to the technique of principal components also. In that technique, we say that we insist that all the variables which have a high degree of correlation, high correlation with one another, can be represented by one single variable. Heteroscedasticity, or absence of homoscedasticity, is the another assumption. That is, we had assumed that UIs were, all the UIs had the same variance, that is sigma square. Suppose different UIs, different UI values had different variances. What will be the consequences? Ordinary least square estimates will remain linear, they will remain unbiased, but their variance is no longer the minimum. Result is tests based on T and F are no longer reliable. We may end up with misleading conclusions. Several tests are available to test whether the data has homoscedasticity or not. Some more common tests are Park's journal test, Glazer's test, and White's journal test. In many cases, the problem becomes manageable with some re-specification of the model. And the third assumption which needs a closer examination is the assumption of autocorrelation. Recall that assumptions about covariance of UI Uj being equal to 0. One significant point about these autocorrelated error terms is that estimates remain linear and unbiased, but they are not efficient. Their estimated variances are biased, and thus T values are inflated. T and F tests are not reliable. Residual sum of squares by degree of freedom do not give reliable estimate of variance of residuals and computed values of R square. And computed value of R square may not be a reliable measure of true R square. For this, tests vary from graphic to Run's test to Darwin-Watson test, which is more, you can say, rigorous. solution usually recommended is generalized least squares. But one thing I would like to point out about autocorrelation. This problem is encountered when we have time series data. And in most of the economic time series, values in any particular time period tend to be correlated with the values in the previous time period and a couple of previous time periods. So, what do we do under such circumstances? We cannot eliminate autocorrelation through any of those techniques. Ultimately, we try to make use of generalized least squares, eliminate whatever possible of autocorrelation, but then, as a last resort, we have to report the Durbin-Watson test statistic values. We have to concede that, well, some autocorrelation is present in the model. There's one more thing which we can do to the multiple regression. Prakash had pointed out that some of the variables may not be precisely measurable. There may be some qualitative variables which play important role. For that, multiple regression model permits us to make use of dummy variables or instrumental variables. We can include qualitative variables in the regression model with help of this technique. We use one such variable less than the number of total qualitative variables which we are including in the model. This inflates the number of variables which are included into the model, but they give us more precise results. Prakash.
Thank you very much, Dr. Bagla. Friends, in this session, we have taken ourselves through the various steps of estimating the regression model and testing the estimated parameters for their significance. We began with a two-variable regression model, presented the estimated results, extended it for the three-variable regression model. We did not go beyond that, and if we were to go beyond that, this manner of presentation would have become too complicated, and we would have made use of our notational benefits of linear algebra and those aspects, including some other things like we did not elaborate on the best linear unbiased estimated test and why do we call it so and things like that. These aspects we can take it up in some of the next sessions. Though the session was very much limited, we have still managed to give you a bird's eye view of the entire aspects that comes under basic econometric analysis. I am really grateful to Dr. Bagla for having joined us this evening, and we hope that this session has been useful to our students. Thank you.
Thank you, Prakash.